Alrighty, well, hello and welcome. We are live. Sorry, a couple minutes behind. I was having Wi-Fi problems, but I believe I have sorted those out, and so we should be good. Should be good for the stream. We have a lovely discussion going on in the live chat about coffee, as you can see. It's always a good way to go. I always like, I always like to be drinking coffee during the stream, but I've also had a lot. I've had a lot this morning, so I'm drinking a Waterloo. These things, the like LaCroix type things, are always a challenge when you're live streaming because you have to try to suppress the burps that inevitably come from drinking carbonated beverages. Anyways, I'm gonna do my best to keep those under wraps. We'll see if you can catch. Now that I'm drawing attention to it, you'll I'm sure it'll be more noticeable. So I don't know why I did that, but anyways, hello and welcome to what are we? Today's Tuesday week 3. Summer is going all gangbusters. As far as news goes right now, just something to keep in mind. I'm sure the exam is kind of looming on everybody's consciousnesses, but our labs, whoa, oh, that's ugly. Lab 6 just went live. All right, so if you are one of those people who likes working ahead, it's available all the way through Lab 6, which means that that Lab 5 also is as well. Now, something to keep in mind with Lab 5, it doesn't always, the lab numbers don't always line up with the chapter numbers, but this is one serendipitous moment where it does. So Lab 5 deals a lot with Chapter 5 material from the textbook, which we're in. We may be finishing it today. Let's see. And Lab 6 also correlates to Chapter 6 material. So before tackling Lab 6, if you're like, oh, I want to get it done, it deals with a lot of the material that we're going to be covering once we hit Chapter 6. So if you take a look at it, it looks bewildering. It's because it's ahead of us lecture-wise. So anyways, that's just something to keep in mind. Okay, I believe that's all the news-ish materials I have going on. We have office hours later today, so we'll be able to get into whatever you guys want to talk about then. But for now, we're going to be possibly polishing off Chapter 5. We may not get through all the rest of it today, but we'll be getting through a bulk of it at least. So anyways, we so up to this moment in time, we have been talking about Lewis structures, and a Lewis structure is a two-dimensional representation of a molecule displaying connectivity. All right, a Lewis structure is a two-dimensional depiction, representation of a model that shows you what atoms are connected to what other atoms, all right? And this was our first really introduction to thinking about molecular structure, about bonding, all that good stuff. The one downside, really, to Lewis structures is this two-dimensional representation. Molecules are not constrained to a two-dimensional plane, right? They exist in 3 dimensions just like we do. And so even though Lewis structures can give us an idea of how the atoms in a molecule are connected, they don't tell us the shape of the molecule. All right, if you want to investigate and examine the 3-dimensional shape of a molecule, you're going to need something else, and that other thing is called VSEPR. All right, which stands for 3-dimensional. Sorry, oh my gosh. Oh my gosh, that's when I read 2 different parts of my notes at the same time and try to say them, mash them up together. There's VSEPR stands for valence shell electron pair repulsion theory. That is what VSEPR stands for, valence shell electron pair repulsion theory. And what VSEPR does is it is our first attempt to explain the 3-dimensional shape that molecules take. All right, this is our first real stab at understanding the shape, the structure that a molecule will have, not just how its atoms are attached. Okay, so this part is going to take a lot of visualization. It may be very challenging. It's challenging for some people. It's not so challenging for others, and it really depends upon how much of a visual learner you are. Something that some students find helpful are molecular model kits. This really, if you are a kinesthetic learner, if you learn by doing as opposed to hearing or reading, then that learning style can be helped by these model kits. You can find them for like $15 on Amazon. They're not required, so I don't require you to buy them. Again, because there are different learning styles. But if you're the kind of person who likes to like build and construct and all that stuff, this you may find this a model kit helpful for this portion of the class. Another thing to keep in mind about what we're about to dive into, this is something that for a normal class, when I say normal, I mean not online. When I teach this in person, I have everyone memorize these things. All right, I have everyone memorize them. And do you have to memorize them? You don't. So I say for this one that memorization, and then I'm gonna add or a cheat sheet. Is recommended here. When you are taking an exam that's testing on this material, I highly recommend that if you do not have these memorized, that you build a cheat sheet for yourself and have that at the ready, because you don't want to be looking these up. You want to be able to spit out the answers, and the construction of a cheat sheet or the use of a cheat sheet will help. Or you could just pack it into your brain. One way or another, these are problems that you don't want to spend a lot of time on in a testing context. Okay, so with that kind of being said, so I've told you that VSEPR is our attempt to explain and understand the 3-dimensional shape of a molecule, all right? But how does it do that, all right? How does it do that? How does this work? And it really comes down to it's this fancy PANS acronym, but there are two letters in this acronym that I want you to focus on. The first one being electron, and the second being repulsion. All right. If you look at an electron is a negatively charged particle. And we know that opposite charges attract each other. Negatives are attracted to positives. When you put two negatives together, these two charges repel each other. Whoa, that is the ugliest line I've ever drawn. Let's see if I can do a little better. These like charges repel each other, all right? These like charges repel each other. And so when you look at the basic idea behind VSEPR is this. Electrons want to be as far from other electrons as possible. All right, electrons want to be as far away from other electrons as possible. That is the core idea behind VSEPR. So when you look at a Lewis structure, for example, let's look at the Lewis structure for CH4. All right. When you look at this drawing, this two-dimensional drawing, you'll notice, so remember that all bonds are made up of electrons, right? You've got electrons, electrons, electrons all up in those bonds, and these bonds, are 90 degrees from each other in this representation. All right, 90 degrees, if you have four groups all attached at a central point, 90 degrees is the farthest. All of these groups can be evenly distributed in two-dimensional space, but it is not the farthest that these three elements can be in three-dimensional space, right? So these, all VSEPR theory does is it asks, well, how far can these things get from each other in three space? All right, how far can that be? And the answer is they can spread out a little bit. So the actual shape, three-dimensional shape, this molecule takes is this. You have two bonds. Let me see. I'm gonna actually pull this down a little bit. So you have two bonds in the plane of the board. In 3 dimensions, these four groups can get 109 degrees from each other. All right, so these things drawn in blue are in plane, all right? They're in the plane of the, I said the board. It's in the plane of the screen or the page if you're taking notes. There's going to be one bond coming out of the page, of the board, of the screen at you. This is in the salmon reddish color. This is in front. And then you're going to have your fourth bond, the last bond, going back behind. And I'm depicting this with green, all right? This green dashed line is behind. All right, and this is how you draw this molecule in 3 dimensions. All right, this is the shape that it takes when it's when those 4 electron groups repel each other, get as far away from each other as possible in 3D. This is the shape that it has. Now, this may be hard or easy to visualize. Again, you may want to use a model kit. This is what they're kind of. It can help you kind of visualize things, or you can search their 3-dimensional representations, image generators online. You can find. But anyways, what we're going to be doing. So this depiction, this is the 3-dimensional representation, and these are what we're going to begin exploring are the shapes that molecules take based on the Lewis structure, moving them, drawing them in 3 dimensions. These are called molecular geometries, all right? And so we're going to be learning about how to analyze a Lewis structure and turn it into a 3-dimensional representation. All the different geometries have different names. And so we're going to be learning how to, based on the Lewis structure, label the geometry and determine what the 3-dimensional shape will be. Susan, I totally see you. This is not easy, especially at first, but this is kind of like an intro to kind of give you a sense of where we're going. But what I'm going to be doing is taking you through this step-by-step systematically, okay, and showing you how you analyze the Lewis structure, determine the 3-dimensional shape, and then draw the 3-dimensional shape. So we're going to be going through this systematically. This is just kind of the introduction, and now we're going to start attacking this one step at a time. All right, so we are going to be looking okay, we're going to be looking at oh, hang on, sorry. Getting a text, just making sure it's not. Okay, so let's start looking at how we can analyze our Lewis structures to determine what the 3-dimensional shape of the molecule is, all right? And there's a few categories that we're going to be looking at. Let's just take this one step at a time. So, the first thing that you want to analyze when you're looking at a Lewis structure to determine its molecular geometry is you want to look at your electron groups. All right? You start by looking at your electron groups together with your lone pairs. All right? Followed by, so based on these 2 things, you'll be able to, well, it lasted. You'll be able to determine 2 things. One, something called the electronic geometry. Followed by the molecular geometry. All right, electronic geometry, molecular geometry, and based on these, we will be able to draw a 3-dimensional representation. All right. Now, I'm going to be unpacking what all of these are, but just so you know, the electron groups around your central atom will determine. Well, we still have a break from sig figs at least. They determine your electronic geometry. The number of lone pairs around your central atom determines your molecular geometry, and your molecular geometry will determine your 3-dimensional shape. All right? So first, we just need to talk about and define what these things are. All right? First off, your electron groups. All right? Your electron groups are the number of atoms and lone pairs around your central atom. All right, the number of atoms and lone pairs around your central atom. That is your electron groups. All right, and just so we're all on the same page. LP stands for lone pairs of electrons. And remember, 2 electrons equals 1 lone pair. All right? 2 electrons equal 1 lone pair. Okay, with that in mind, let's start looking at Lewis structures and their 3-dimensional shape, all right? So first, we're going to look at carbon dioxide. Oops. Nope. Whoa, I don't want that in blue. CO2. All right. Now, if you want, for practice, you can go back and draw out the Lewis structures for all of these step by step. And if you want that practice, you can have it. I'm not going to do that here for the sake of time. We spent all last lecture covering how to draw Lewis structures, and now we need to learn how to take those Lewis structures and determine their molecular geometry. So I totally encourage you to practice it step by step, but right now, for the sake of time in this lecture, I'm just going to draw out the Lewis structure. So you can pause the video here if you're watching or rewatching. See if you can come up with the correct Lewis structure. But this is the Lewis structure for carbon dioxide. All right. Now, when you look at the number of electron groups, remember, the number of electron groups are equal to atoms around the central atom plus lone pairs. All right. And here, our central atom of carbon dioxide is carbon. And there are 2 atoms, 0 lone pairs. So we have a total of 2 electron groups. 2 electron groups, all right? Once you know the number of electron groups around your central atom, and something that's important, it's atoms, not bonds, right? It doesn't matter that the oxygens are double bonded, it doesn't matter if they're single bonded, it doesn't matter if they're triple bonded. We're just looking at the groups. So 2 atoms, 0 lone pairs, 2 electron groups. Once you know how many electron groups you have, you automatically know the electronic geometry. Whenever you have 2 electron groups, your electronic geometry is something called linear. All right, you have a linear electronic geometry. All right. Now, we have 0 lone pairs. All right. Whenever you have 0 lone pairs, your electronic geometry and molecular geometry will be the same. So with 0 lone pairs, it means our molecular geometry is also linear. All right. Something to keep in mind. I should have stated this earlier. Spaced my mind. I just saw it now in my notes. The electronic geometry, just so that we're all on the same page. The electronic geometry is the shape of the electron groups around your central atom. Oh, I'm just going to scoot this up a little bit. So the shape of the electron groups around the central atom. All right, and the molecular geometry is the shape of the atoms around the central atom. All right, so the shape that the electron groups make is the electronic geometry. Whenever you have two electron groups, it's linear. The shape of the molecular geometry is the shape all the atoms around. So with the electronic geometry, you look at all electron groups. With the molecular geometry, you only look at the atoms. That's why when you have 0 lone pairs around your central atom, your molecular geometry and electronic geometry are the same. All right? Now, the way you draw the three-dimensional representation of a linear molecular geometry is, I'm sure as you can imagine, a straight line. So this is what the molecule looks like in 3 dimensions. It's just one straight line. Being a straight line, it's 180 degrees, right? That's what the molecule looks like in 3 dimensions. This is one of the rare examples. The linear molecular geometry is an example where the Lewis structure actually does look like the 3-dimensional shape, but as we'll see moving forward, that's not always the case. All right? So there's our first example of taking a Lewis structure, labeling the molecular geometry, and using that to draw a 3-dimensional representation. All right? Let's do another example. Let's look at, for your consideration, let's consider the molecule formaldehyde. All right? Now, when you draw the Lewis structure of formaldehyde, right, it looks like so. All right, there's our Lewis structure. Now, when you look at the number of electron groups around our central atom, we know electron groups are atoms plus lone pairs on our central atom. Our central atom here has 3 atoms attached, has 0 lone pairs, which means that it has 3 electron groups. With 3 electron groups, whenever you have 3 electron groups, your electronic geometry, the shape that the electron groups make around the central atom, is called trigonal, planar. All right? 3 electron groups around your central atom gives you a trigonal planar electronic geometry. We have 0 lone pairs, which means that our molecular geometry will be exactly the same as our electronic. Trigonal planar is our molecular geometry. All right. Now, a trigonal planar molecular geometry looks like this. You have your central atom, but then your 3 electron groups are all 120 degrees apart. They're all in the same plane, so we draw them all with lines, and they kind of make this little peace sign. When you compare this to the bond angles in the Lewis structure, you can see that these are all right angles. They're 90 degrees, but the 3-dimensional shape has all your bonds in the same plane. It's planar, but they're at 120 degrees from each other. So that is the 3-dimensional representation of the trigonal planar molecular geometry. Cool? How you guys doing? Okay, well, it's all silent on the home front. I'm going to assume you're doing okay till I hear otherwise. Let's look at another example. Let's look at an example where we actually have a lone pair around our central atom. You may be going, well, what happens when we don't have 0 lone pairs? And I am so glad you asked. Let's look at the molecule. Whoa. Not in blue, please. Nitrite, one of our polyatomic ions. The Lewis structure for nitrite. Yes. Okay. Great questions. First, what Kate just said, I'm going to be watching this over. I do want to say repetition. Repetition is the key with this stuff. Karenessa is asking how do we know it's 120 degrees? Well, first off, I just want to say the angles that I'm giving for this class, you do not need to have it memorized. I don't require the book doesn't teach you what the bond angles are. In Chem 400, you totally will. But here I'm just showing you the difference between the Lewis structure and the VSEPR geometry. So you can see that the difference between 90 and 120 degrees. But to answer your question, there's 360 degrees in a circle. If you divide that up evenly by 3, each bond angle would be 120 degrees. And then Parthana, we know that it has 3 atoms attached to it based on the Lewis structure. So the reason why we have 3 atoms comes from the Lewis structure. And you'll always have a Lewis structure to analyze when you're determining your molecular geometry. Carenza. So that's where the memorization comes in. Three electron groups is defined as three electron groups is defined as trigonal planar. So that information that I'm presenting is stuff that that should be memorized. And well, so actually here, since we're getting some questions, let me bump back. Prothana, actually, oxygen is only bonded to one atom. But all that matters for the geometry is the central atom, which is carbon in this molecule. Yep. Karenza, exactly right. 3 electron groups, 0 lone pairs is defined as equals trigonal planar. Yes. Totally. That is what it's geared towards. Brianna, that's exactly why I'm laying it out like this. Parthana, not for this molecule. But we will see examples. Where it does. Alright, we'll definitely get to examples where there's 4 atoms around the central, but for this one, it only had 3. Okay, let's These questions have been awesome. Thank you for vocalizing them, asking them. Let's take a look at this next example. Now the Lewis structure for nitrite looks like this. Okay, Prathana. I totally get where you're coming from. For VSEPR geometries, never count the bonds. Never count the number of bonds. Just look at the number of atoms attached plus the number of lone pairs. All right, so you never look at the number of bonds around the central atom. You only look at the number of atoms attached. So even if you look at this example, nitrate has 2 oxygens attached. It doesn't matter that one is double bonded and one is single bonded. You only look at the number of atoms. All right. So let's look at the number of electron groups here. Nitrite has 2 atoms plus 1 lone pair. So we have a total of 3 electron groups. All right. Now, anytime you have 3 electron groups, all right, anytime you have 3 electron groups, your electronic geometry is always going to be trigonal planar. All right, trigonal planar. But here, for the first time, we actually have one of our groups around our central atom. Awesome. One of our groups around our central atom is a lone pair, all right? And the lone pair changes the molecular geometry, all right? Now, the electronic geometry is trigonal planar. That's because the electronic geometry views all groups equally. It doesn't matter if it's an atom or an electron. Lone pair. Whoa, that is ugly. I'm just gonna. It looks at all the groups the same. All right, and that is the electronic geometry. All right, but the molecular geometry does not look at the shape of all the electron groups make. It only looks at the shape that the atoms make. So to draw the molecular geometry, draw out the electronic geometry like I've done here, but then we're going to, for the molecular geometry, we're not going to draw the space that that lone pair takes up. We're only going to draw the shape that the atoms make. All right, so you draw out the electronic geometry, and then to get to the molecular geometry, you don't draw out the lone pair on the central atom, you just draw everything else exactly the same. All right, now hopefully that makes sense. This is the 3-dimensional representation of nitrite. And the molecular geometry, you can see it kind of looks like a line that's been bent when you look at the molecular shape. And so the molecular geometry of a trigonal planar molecule with 1 lone pair is bent, is the name of the molecular geometry, because it kind of looks like a bent line. And again, as we discussed before, this is based off a definition. Whenever you have a 3 electron groups around your central atom, but one of them's a lone pair. So 3 electron groups, one's a lone pair. Your molecular geometry is defined as bent. All right. So this is a bent molecular geometry. All right. Let's take a look at another example. All right. So new example. Let's examine the molecule SiH4. All right. Now, if you draw the Lewis structure for silicon tetrahydride, this is its name. We'll talk about naming these at the end of this chapter. The Lewis structure comes out like so. Now here we have 4 atoms attached to our central, 0 lone pairs, which means that we have 4 electron groups around our central atom. Whenever you have 4 electron groups around your central atom, your electronic geometry is tetrahedral. All right? You have a tetrahedral electronic geometry. Whenever you have 0 lone pairs, your molecular geometry is the same. Tetrahedral. Now, how do we draw a tetrahedral geometry? This is the one that I gave an intro with CH4. It was a tetrahedral geometry. You draw a tetrahedron like so. Oh, wait, it's not carbon. We've got silicon here. You draw 2 of your 4 groups in plane. All right, this is in the plane of the board, page, what have you. You have 1 bond or 1 electron group that you draw on a wedge. This is in front. All right. The final electron group you draw with a dash, a series of dashed lines, and this electron group is behind the plane of the board or page or what have you. So this is the 3-dimensional representation of the tetrahedral molecular geometry. I drew this in color with the in plane, in front, and behind kind of highlighted, hopefully to help you visualize it a little bit. One of the things that I do is I'll take my pencil and I'll put it up against my screen to be like, okay, that bond is coming at me, and then I'll kind of put it behind the paper and go, okay, that bond is going away from me for the green one. So green is away, the red one is at me, and then the 2 blue ones are kind of perfectly in the plane of that piece of paper. All right, so this is the tetrahedral geometry. 4 electron groups, 0 lone pairs, tetrahedral. All right? Now, what is going to happen? How is our molecular geometry going to change once we start adding lone pairs? And that's what we'll look at with ammonia, NH3. All right? Now, ammonia's Lewis structure, I'm going to give myself just a little more space here. Looks like this. All right. So it looks like so. And when we look at the number of electron groups around our central atom, here we have 3 atoms, 1 lone pair, so we have a total of 4 electron groups. Now here's the thing. Well, 4 electron groups, one of those electron groups is indeed a lone pair, all right? Now 4 electron groups means that the shape that these four groups will make around your central atom will be tetrahedral. All right, tetrahedral. Now, you can start drawing a three-dimensional shape just knowing the electronic geometry. Because if you have a tetrahedral geometry, you will have two electron groups in the plane of the page you're drawing on, one electron group coming out, so it's wedged, one electron group going back, so it's dashed. All right? Now here, three of our electron groups are hydrogens. It doesn't matter where you put them. One of our electron groups is a lone pair. All right, so you put that on one of the spaces as well. Now that is the electronic geometry. We want to know what is the molecular geometry like. And to get from electronic to molecular geometry, you redraw things exactly the same, except you don't draw the lone pairs on your central atom as taking up space. So drawing that now, we would have one H on a straight line, one H on a wedged line, one H on a dashed line, and the fourth group, that lone pair, is just going to be two dots on your central atom. All right? This is your three-dimensional representation. Now, the molecular geometry for this shape is the shape that it makes, and if you have a model kit, you could build it to see this, but it kind of looks like, whoa, where's my camera? There we go. It looks like a pyramid. If this is where the nitrogen is, it like makes a period where there's a hydrogen, well, I'm moving off camera, a hydrogen at each base, all right? So it's kind of like a pyramid with, there we go, 1, 2, 3 vertices down at the bottom. So the name of this molecular geometry is trigonal pyramidal. All right, don't confuse this with trigonal planar. This is trigonal pyramidal because it makes a pyramid with 3 vertices at its base. All right, so 4 electron groups, 1 lone pair is a trigonal pyramidal geometry. How are we doing on time? Okay, we're doing all right. Let's look at our final molecular geometry. All right, this will be our last molecular geometry, and there can be no more fitting place to end this than looking at a molecule of water. So if you draw the Lewis structure for water, it'll look like this. All right, when you look at your number of groups around your central atom, you have 2 atoms attached, 2 lone pairs on your central atom. So we will have a total of 4 electron groups. 4 electron groups, 2 lone pairs. Now, because we have 4 electron groups, we can already start drawing the 3-dimensional representation based on its electronic geometry. Right, the electronic geometry here is tetrahedral. Tetrahedral, and every tetrahedral electronic geometry is the same. You have 2 groups in plane, 1 group wedged coming out at you, 1 group dashed going back at you. All right, and you can put your lone pairs or hydrogens anywhere. I'm going to put them here because I think it's going to make visualizing this easiest. All right, now not even knowing what the molecular geometry is, we can already draw our 3-dimensional representation, because the 3-dimensional representation of the molecular geometry will look exactly like this does, except we don't draw the lone pairs taking up space. So the 3-dimensional geometry, the 3-dimensional representation of a water molecule will look like this. We don't show the lone pairs. We just show the atoms. And if you look at this geometry, again, it kind of looks like a line that got bent, and that is the name of the molecular geometry. When you have a tetrahedral electronic geometry with two lone pairs, your molecular geometry is bent. All right, so this is a bent molecule again because it looks like a bent line. Your book also calls these angular. I just call them bent because that's how I grew up. The book will say angular and then in parentheses bent, but it's the same thing. Okay. Those are our VSEPR geometries. All right? That is how you analyze a Lewis structure. That is how you determine your electronic geometry, your molecular geometry, and how you draw the three-dimensional representation for the molecular geometry. All right. What I have to say about all of this. So, if you're feeling overwhelmed right now, we just went through a ton of information. All right. We just covered a lot of material in a relatively short amount of time, and this is the type of thing that doesn't. You won't be able to interpolate. You won't be able to kind of assimilate this into your way of thinking without a lot of repetition. So here's what I would recommend. Oops, no. I would recommend creating. I would create your own cheat sheet with everything that I was drawing out. The Lewis structure, electron groups, lone pairs, electronic geometry, and molecular geometry. Build one yourself. Like make a grid, create one, because the process of making one will help you study. It'll be part of that studying process. And then once you have this assembled, look at the practice homework. For chapter 5, I assigned a ton of problems to give you guys enough repetition to kind of practice this, get this information kind of into. This is one of those things that you're only going to learn it if you start doing problems. So build the cheat sheet and then use it, and that process will kind of help get this information. That repetition will get this info into your head. And then a quick FYI, lab exercise 5 is like 90% VSEPR. All right, 90% VSEPR. So you can work on lab exercise 5. There's no video. It's a dry lab. Usually it's building molecular model kits. You can work on lab exercise 5, or I should say working on lab exercise 5 is studying this material. So I would also direct you there. Even you can attempt those things maybe before the practice homework, because that's an assignment that's due, so you can kind of kill two birds with one stone, work on lab exercise 5 and kind of practice this these molecular geometries. All right. Now we've got 2 topics left in chapter 5 to cover. The first one is one of them's a little harder, and you have to feel versed in the you have to be comfortable with molecular geometries. The other one is more straightforward and easy. So I'm going to do the easier one today, and then tomorrow we'll hit up the molecular polarity. And what I would recommend is practice your VSEPR geometries today, because comfort with VSEPR geometries is going to be crucial for understanding molecular polarity, assessing molecular polarity. So all of that is coming at us tomorrow like a freight train, much like today's lecture. But for now, let's pause, shift gears. We can talk more about VSEPR geometries in office hours to kind of get some reps in. I can make some problems, have you guys analyze some stuff if you want, or you can ask me questions about stuff you're working on. But let's close today by talking about naming covalent compounds. All right, naming covalent compounds. Now, we've talked about naming ionic compounds, right? It's cation name plus anion name with an "ide" added at the end. The trick with covalent compounds is we can't get away with just name of one atom. Well, first, there are no anions or cations, right? The second tricky thing with covalent compounds is if I asked you to name this, here, let's actually do a slightly different example. And I asked you to name this, we couldn't call the first one carbon hydride because the second one is a different model and it only has carbon and hydrogen. So for ionic compounds, they always have the same ratios. Covalent compounds, the atoms can combine in different ratios. And so we have to explicitly state how many of each atom are present in the covalent compounds, all right? So the way you name covalent compounds is like this. You state up, you give a prefix, and then atom 1, followed by another prefix and atom 2, and then atom 2 you still add, after atom 2 you still add that ide ending, all right? And this is how you name covalent compounds. The prefixes involved are fairly simple. You're probably already familiar with them. If you have 1, the prefix is mono. If you have 2, the prefix is di. 3 is tri. 4 might be a little different. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. All right? And so for our first example, C2H6, you would name this as dicarbon hexahydride, because you have 2 carbons and 6 hydrogens, all right? Dicarbon hexahydride. The second example, C3H8, would be, let's see, 3 is tri, so this would be tricarbon, cabin. It sounds like I'm from the East Coast. Cabin. Tricarbon. And then 8 is octa, tricarbon octahydride. All right, naming these, very straightforward. You're just making a laundry list of atoms, essentially. There's only one irregularity in this system, and that one irregularity is that prefix, that first prefix. If there's only one atom, if your leading atom, if there's only one, you never use mono for the first prefix. And you may be going, oh, that's so lame. That's one new weird quirk I have to memorize. That's so lame, I don't like it. Here's the cool thing. You actually already knew that rule, and I'd like to prove it to you. I would like you to name the following compound if you can. Trying at home, can you name this guy? CO2, yes, you absolutely can. This is carbon dioxide. You did it without even trying, right? Why didn't you call it monocarbon dioxide? Because nobody does, right? It's carbon dioxide. If there's only one of the first atom in your name, you never include mono. And you're going, well, but what about remembering the second one? I need a mono. How am I supposed to remember that? Well, you already knew that rule too. Try at home to name this compound. And this is, you guessed it, carbon monoxide. If there's only one of that first element, you never include mono. But guess what? If there's one of the second element, you always include mono. All right. So, yes, this is for non-charged covalent compounds. Karenza, that is a great question. Each polyatomic ion has its own special name. That does not follow any rules. We just gotta memorize it. All right, that's all we can do with polyatomics. They don't follow any set of rules. These are for non-ionic compounds, non-ionic covalent compounds, because, Corinza, as you pointed out, our polyatomic ions are covalent compounds, but these are for the non-ionic ones. The polyatomics just have their own special name, each one. They're like demons, each with their secret name. Although I guess it's not that secret. We know the polyatomic ion names. All right. Okay. We covered a lot of material this lecture. If you're feeling overwhelmed and that's causing you to feel stress, remember, the only way to deal with that is to study. So I'm going to go ahead and call lecture here. We're going to draw things to a close. We didn't quite finish Chapter 5, so we will talk about molecular polarity tomorrow. Between now and then, I strongly encourage you to study your VSEPR geometries, because molecular polarity will not make a lot of sense if you are unfamiliar or feeling shaky with your molecular geometries. All right, so let's hit that. I'll be back here in 30 minutes to start office hours, and we can talk about everything that you want to talk about. and more. So I'll catch you guys in a few. And for the rest of you who won't show up in office hours, I'll catch you guys tomorrow in lecture. Later.